Okay, so the decision region that we get by using the maximum likelihood detection becomes identical to what we get by using minimum distance decoding. And so minimum Euclidean distance decoder would obviously have two decision regions. This is the region R1. Not sure what is this. I don't like this. So decision R1 is this decision region over here. So this is the decision region for bit 2, R2. This is the decision region for bit R1. And the decision region are separated by this red colored boundary, which has to be a perpendicular bisector of the line, this black line, which are connecting these two constellation points. And it's pure geometry. You should be able to convince yourself that all the points that are falling in the region R1 of this red line are closer to S1 compared to S2. And similarly, all the points of this plane which are falling on the other side of the red line are closer to S2 compared to S1. Okay, so now I have a question that what is the expression for the probability of bit error, bit detection error or demodulation error for BFSK? So we should be able to answer this rather quickly based on what we have observed earlier. Can anybody tell me this answer to this question?
So in similar manner, we can derive as we derived for BPSK error.
Yeah. But what is the answer? We don't need to go through the whole derivation, remember? From the last time, do you remember what we concluded about the theoretical expression for the probability of bit errors, especially for the constellations which have only 2 points?
Q of A by sigma n.
Q of A by sigma n. But what is A here? There is we haven't used the notation A here at all.
Equals to root EB by N0.
Q of Isha is giving the right answer. Q of square root of EB and not. Can you elaborate on this, Isha? Why this is Q of EB by N naught?
Yes, sir. Because we have derived that it is D upon 2 sigma. And
Correct.
Root ES and root EB is the same, and N0 is number of bits per total number of bits.
So all in this expression we need to figure out is what is D? What is the distance between the two constellation points? That to figure out. So who can tell me what is the distance between the two constellation points?
2EB.
D squared is 2AB. 2AB, yes. So if I plug, if you recall, q of 2 divided by square, sorry, so d square divided by 2 and not. So here d square is 2eb. So in this equation over here that I had just written, so this is a mistake. This should be d squared divided by 2 and not. And d squared is equal to 2eb, and so the answer that Isha gave comes about. Okay, so this is kind of very straightforward. You know, Isha was able to give this answer right away, whereas someone else said that we can alternatively derive this bit error probability using the same approach that we had for BPSK, where we went through that entire entire uh, integration of the conditional PDF. The problem with doing that here for BFSK is that the conditional PDFs become two-dimensional, right? Because now the noise is two-dimensional. Constellation points are two-dimensional, although one of the dimension is 0. It is indeed the case that there are two constellation points on two different dimensions. And the noise, as we said last time, will not be having this nice property that one of the two coordinates is 0. And so we have to kind of integrate the noise over, first of all, the noise PDF will become two dimensions. It will be not just P of n anymore. It will be, so this won't be the case. It will become P of Ni and Q. And then in the bracket will be again Ni and Q. So it will become a two-dimensional PDF. If we assume that this joint PDF Ni and Q of noise, Ni and NQ are independent, then at least we can simplify and say it will be P of Ni times P of NQ. Maybe we can make this simplification, but still, it still will remain two-dimensional. And now we have to do the type of integration that we did, the conditional PDF that we integrated on the opposite side of the decision region that we did for BPSK. We have to do the same thing, except that integration has to be performed. Let us say we are trying to determine the probability of error when bit 0 was transmitted. Then the probability of the error will depend on the conditional PDF of the noise, this two-dimensional PDF, over this entire region on this side of the decision boundary, right? Because that is going to tell us what is the probability of error, the received two-dimensional vector falling on the wrong side of decision boundary. So that integration becomes more challenging. It's not that we cannot do it, but it will take us some effort, much more effort than what we had to do for BPSK, where it was just nice one-dimensional PDF. The cool thing about looking at the modulation scheme in terms of this constellation diagram is that instead of doing that two-dimensional integration, we can right away employ this rule that for binary modulation, the probability of error has to be given by the Q of square root of d squared divided by 2 and naught. And so now it becomes just a matter of figuring out what d squared is, which is 2 times EB from Pythagoras theorem. And so then we don't have to do any such integration. How did we say that it is Q of square root of d squared divided by 2 and naught? What was the rationale for us to make this equation.
EB was 2a square, and so a is d by so divided by 2.
Yeah, Abhay, maybe something like that. But more specifically, what I want you to think about is that the probability of error doesn't depend on where the constellation points are located in this plane, in this IQ plane. We went through that example last time. If you recall, we had 3 different constellation schemes. And we concluded that the absolute location in the plane doesn't matter in terms of the performance of that scheme. What matters is the distance between them. If the 2 constellation points are closer together, then it is obvious that one can be confused for the other. If the 2 constellation points are very far apart, then the chances are that for the same noise level, you will not have difficulty in confusing one for the other. Basically, the performance, which is how frequently you end up making errors, depends on whether the noise can push a transmitted constellation point on the wrong side of the decision boundary. And then once you think about that aspect of the accuracy of the modulation, we kind of logically conclude that the ability of the noise to push us on the wrong side of the decision boundary depends only on the distance between the 2 points. Just the same way the decision boundary is the perpendicular bisector of the line connecting the 2 points. It doesn't matter where the 2 points are. The decision boundary is always halfway between them. So same way, the performance also depends only on the distance between the 2 points. And from the BPSK example, we concluded that the performance of the BPSK can be written as Q of square root of B squared divided by 2n. Specifically, the performance of BPSK was Q of A divided by sigma n. So this is what we concluded mathematically. And we said that sigma n is n naught divided by 2. Sigma n squared is n naught divided by 2. And A was, what was A? A squared was, or even for BPSK, we can say A was D divided by 2. And so once we plug those expressions in Q of A divided by sigma n, we came up with this equation over here. So this is a very powerful, very elegant way of simplifying the analytical expression of the performance of the system. And the nice thing is that now in MATLAB, suppose if you simulate this BFSK and you obtain the probability of detection error for BFSK in MATLAB through your simulation, you will observe that if you didn't make any programming error, your performance result will exactly match Q of square root of EB by N. And this expression we derived completely analytically. So now one thing that I want to mention is about those perpendicular directions. Who recalls why we are able to draw this perpendicular directions x and y which are perpendicular to each other for BFSK. I gave you a brief answer to that last time. Does anybody recall that?
We consider them as vectors, and their dot product is 0. That's why they're perpendicular.
Yes. So what does it really mean? Okay, so let us look at that. So for BFS, so some detailed model of BPSK. And so when I say detailed, I'm going to bring in the electromagnetic waves. Okay, so bit x equal to 1 in BFSK is transmitted as. So this is now a more realistic model of the actual signal that gets transmitted by the modulator. So it will be transmitted as S of t. So now we are actually talking about a physical waveform as a function of time. So this is the time variable. S of t is, what is it? It is square root of EB times F1 of t. If x is equal to 1. Okay, so maybe I should not have this part. Let me strike it out. So the BFSK modulated signal is written as or transmitted as square root of EB F1 of t if x is equal to 1, and if x is equal to 0, it becomes, oh sorry, this F1 by the way is not frequency. Okay, I should use another notation so as to not confuse with the frequency. Let me call it G1 of t. And this will be transmitted as G2 of t if x is equal to 1, if x is equal to 0. So if incoming bit is 1, then we take some waveform G1 of t and multiply by square root of EB. Basically, we amplify it so that its amplitude becomes square root of EB times the original amplitude. If it is G2 of, if x is equal to 0, then we replace G1 with G2. And we again multiply by square root of EB. And then the transmitted signal becomes that. Okay. Now, what is G1 and G2? So I can say that G1 of t is an electromagnetic. So I will actually make it proportional, not equal. G1 of t is proportional to cosine of 2 pi f1 of t. Now this f1 is the frequency. It's the same frequency that we had mentioned on the previous slide. And G2 of t, as you can guess, would be a cosine signal. It will be proportional to a cosine signal at frequency f2, 2 pi f2 of t. As you know, this cosine function is an oscillating waveform similar to your electric field or magnetic field, which actually gets transmitted from the antenna. So this is something that actually gets transmitted from the antenna. If you are using, let's say, a 4G phone, this F1 could be, I don't know, 2.5 gigahertz. And this F2 could be 2.5 gigahertz plus maybe another 100 kilohertz or something like that. So these are actual physical frequencies. If you take your phone to a communication lab and connect your phone to an equipment which can actually plot the electromagnetic wave that is being emitted by your antenna of the phone, you will actually see this type of signal. Cosine of 2 pi f1, cosine of 2 pi f2 is a function of time. Now, I made them proportional. So if I want to remove the proportionality, I would need to replace it by some constant. Now that constant of proportionality is determined by, so I'll say the conditions on G1 and G2T are, one, they are unit energy. They are unit energy signal. So what this means mathematically is that if I do integration from 0 to the symbol duration, T-sim. Remember, this is one particular symbol that we are transmitting. Right? If I have one bit to send, I will send either G1 of t times square root of EB if that bit is 1. Otherwise, I'll send square root of EB times G2 of t. So this is only for one symbol. So G1t and G2t, you can think of the time domain span as going from 0 to symbol duration in seconds. So we have to integrate 0 to T-sim period over that much period. G1t magnitude squared. I don't need the magnitude sign. I just, because I'm squaring it, I don't need to take absolute. Squaring operation will always do that. So G1t squared dt should be equal to 0 to T-sim G2t whole squared dt. This should be equal to 1. That is what I mean by unit energy. When I do this integration, I am calculating the energy of each of these waveforms. And the one condition is that there should be unit energy. And so you have some unknown here, constant of proportionality. You plug it in and make G1t equal to, let's say, k times cosine of 2 pi f1t. Now you take that whole expression k times cosine, plug it into this, set it to equal to 1, and then solve for k. Okay, so that's how you will get this constant of proportionality. Then actually there is a condition which will actually make clear why these two signals are perpendicular. So the second condition is that the following integral, shoot, this integral has to be 0. This is the second g1t times g2t dt integration from 0 to t sin. Now, it turns out that the way I have formulated g1 and g2 as proportional to f1 and f2 of cosine, it turns out that if you plug these expressions, and you can actually make constant of proportionality to be a variable, some constant k. If you plug this, those two expressions here, basically multiply cosine of 2 pi f1 times cosine of 2 pi f2, and then carry out this integral. And if so I'll say this is the case for the given, this is the case for the given g1 and g2 provided what? Provided that this cycle duration of this waveforms, so cycle duration will be 1 over f1 and 1 over f2, is much, much smaller than the symbol duration. So there is this assumption that these two frequencies are kind of high compared to the inverse of the symbol rate. With this assumption, you should be able to prove this. And all you need is simple trigonometry identities. Because g1 is cosine 2 pi f1t, g2 is cosine of 2 pi f2t. You multiply them, then you invoke the trigonometry identity in terms of what happens when you multiply two cosine terms. And then you invoke this condition, and you will see that it becomes 0. I would say when you do the mathematical derivation, it may not be, your answer may not be exactly 0. It will be approximately 0. Okay? Which is good enough for our case. By the way, it will be exactly 0 if, in case, 1 over f1 is equal to t sin, or 1 over f2 is equal to t sin. But otherwise, you will get an answer which is approximately 0. So this requires nothing other than your 11th grade trigonometry. And I ask that you convince yourself that this is the case. And so this particular equation that we are looking at is the reason why I am drawing f1 and f2 on two perpendicular dimensions. Because I'm going to now think of g1t as sort of a vector. Kind of a vector. It's not real vector because it's actual signal. It's a function of time. So vectors are not like that. But in math, we can kind of let our imagination run wild, so to speak. And so we will think of them as two different vectors. Another vector. And then with that, we will say that this whole integration, we are going to think of it as the dot product. of G1t and G2t. And I'm already telling you that this integral is at least approximately zero, if not exactly zero. And let me see. Yeah. So it will be approximately zero, if not exactly zero. And so we conclude that the dot product between these two vectors is zero, which means that these two vectors are perpendicular to each other, which means that over here, if I now write x-axis as nothing but g1 of t and y-axis as nothing but g2 of t, then my constellation diagram becomes exact. Why does it become exact? Because remember, the transmitted signal is square root of EB times G1 or square root of EB times G2. And that is what exactly this says. Y-axis is G2 of T, and we are multiplying it by square root of EB. And so if I abstract out G2 of T, then all that I need to say is the coordinate, which is 0 and square root of EB. I am not, when transmitting bit 0, signal S2, I am not making use of G1 of T at all. And therefore, the corresponding multiplier becomes 0. I multiply G1 by 0 and G2 by square root of EB, and I get this constellation. And similarly, I get the constellation point for X1 as square root of EB and 0. So this is kind of, we are kind of getting a little bit deeper into the waters, okay? Maybe we were at the baby swimming pool when we just simply drew the constellation diagrams without worrying about what this x-axis and y-axis are and why they are perpendicular and all that. So this here, I'm kind of giving you a little bit more flavor of the real design or the real scheme. I'm bringing in the electromagnetic transmission that is happening from the antenna, and I'm showing you that with that, through these two requirements or the conditions, I can write the constellation points in the manner that I had shown you earlier. Okay. Now, what about QPSK, right? So QPSK, if you recall, this was the constellation diagram. Here again, I have two perpendicular axes. So what are this? Remember, for QPSK, I didn't say that we are using two different frequencies. Actually, we are using only one frequency for QPSK. Then for one frequency, how can we have two perpendicular dimensions? Right? I mean, for BFSK, let's say that you accept what I said, that if G1 of t is cosine of 2 pi f1t, G2 of t is cosine of 2 pi f2t, multiplied by some proportionality constant that you can be able to figure out, given that requirement number 1. When I tell you that if I multiply G1 of t and G2 of t, integrate from 0 to t sim, I get almost 0, or if not exactly 0. Without doing the math, let's say that you accept what I'm telling you, then from that analogy I gave you, think of G1 of t as a vector, G of t as a vector, and that integration operation as a dot product, then you can kind of maybe, your mind may be a little bit resisting. You may be saying that, okay, this is too much for us to absorb, but generally you can say that, okay, fine. fine. Maybe it makes sense that I can draw G1 of t and G2 of t as two perpendicular vectors. But here I have only one frequency f. So what can I do? I mean, how can I have two different dimensions? So I will quickly write that, how we got two dimensions for QPSK. I'll quickly write it here now. This is detailed model of BFSK, and this is the requirement for BFSK. So for QPSK, detailed model of I still need G1 of t and G2 of t. That I need, because it is those two waveforms which are allowing me to create two perpendicular dimensions or two perpendicular axes. It turns out that for QPSK, G1 of t is proportional to cosine of 2 pi f t. Remember, now I have only one frequency, so I'm just going to denote it as f. I don't need to do f1 and f2 anymore. So G1 of t is kind of similar to what we had for binary frequency shift key. But G2 of t, it turns out I can make it as proportional to, sine of 2 pi f t. And magically, I get to say that G1 and G2 are, although they are actual electromagnetic waveforms, I can think of them as perpendicular vectors. First of all, the length of G1t and G2t as vectors, the lengths of these two vectors is equal to 1. This is same as our requirement 1 of the previous slide. And this will allow again calculation of the constant of proportionality. And 2, the two vectors, they are not actual vectors, but we are thinking of them as vectors. So I'm putting that in this apostrophes. These two kind of quote unquote vectors are oriented 90 degrees apart. So this is our second condition, meaning that if I do the same integral, G1t, G2t, the product integrated over 0 to t sim, I will get 0. And so you can again do the math. The math is not going to be difficult for you. And you will convince yourself that both of this requirement, the first condition is just a way for you to determine the constant of proportionality. And okay, fine. I'll quickly ask you this question. If you are able to answer, it's fine. Otherwise, I'll answer it myself. Anyone has an idea of what this constant of proportionality will be given this requirement 1? Can anybody do the math in their mind very quickly and tell me what the constant of proportionality will be?
It should be 1.
Okay, so I'll give you the answer.
1 by root 2.
No. Okay, so the answer is the proportionality is as proportionality, which will make sure that G1 and G2 as vectors of unit length, or more specifically, uh, this integral G1 square T, G2 square T integrated over 0 to 2 sim becomes equal to 1 when G1 and G2 are this cosine 2 pi f1 to pi f2, or G1 and G2 are this cosine and sine waveforms. In either case, the constant of proportionality let's see,
Will be root of frequency by 2.
no, it will be 1. So square root is there, that part is right, and somebody said square root of 1 over 2. That I think is right. Okay, I mean, I'm trying to do the math in my mind, but one part is a little fuzzy. So this part, I am not fully sure, but it's either 1 over square root of 2 sim, or maybe this 1 over square root of 2 is not there. It might be just 1 over sim square root. If I have to guess, I will say that this is the right answer, but not having done the math right now myself, I'm wondering whether it could be this. Okay, so it's basically square root of 1 over t sim. Maybe you have to multiply it again by 1 over square root of 2. That part will figure it out later on. But this is the constant of proportion. And then later on, you should be able to prove to yourself that that other integral G1 and G2 product integrated over 0 to 2 sim is also becoming 0. Okay, so this is the detailed model of QPSK. And now, if I am transmitting, let us say, this particular symbol, which I will transmit if I get 2 bits as 1 and 1, then this will now be a superposition of G1T and G2 of T. G1 of T is some constant of proportionality times cosine of 2 pi f t. G2 is same constant of proportionality times sine of 2 pi f t. So I am actually adding cosine and sine waveforms together. Okay. So then the result will be a summation of cosine and sine, which I am adding together. And that is the actual physical radio frequency electromagnetic wave that I will actually transmit. When I am transmitting bit 1, 1 over one symbol duration, 0 to 2 sim, then t sim to 2 times 2 t sim, the second symbol duration, maybe I'll get 0, 0. Then I will again take those same two G1 and G2 that we have specified just now. But now I will multiply them by different coefficients, minus square root of 1 over 2 and plus square root of 1. Something like that, right? So how I am multiplying G1 and G2 are given by this mapping diagrams. And then the result will be the summation of the weighted summation of G1 and G2 as indicated by this constellation point. Okay, so that is kind of, I think I still want to maintain focus on this simplified model and not get into this aspect, which is a little more detailed aspect. We will do this later on, but at least this kind of is giving you kind of a preview of what we are going to do towards the later part of this modulation topic. So coming back to our simplified model, remember we started with BPSK. We drew the constellation diagram for BPSK. Then we went over to QPSK, which was instead of one dimensional, it became a two-dimensional constellation diagram. Then we considered binary frequency shift key, which was also a two-dimensional diagram, but now I'm transmitting only one bit at a time. There are only two constellation points. So for BPSK and BFSK, I transmit only one bit per symbol. For QPSK, when I'm transmitting a symbol over this T symbol seconds, I'm able to transmit 2 bits. Every symbol is kind of a vehicle which has 2 bits inside it. What if I'm more ambitious? What if I want a vehicle, maybe a car, maybe a truck, which instead of 2 bits, it can carry 3 bits, or 4 bits, or 5 bits? Well, that is where we get into further generalizations. So I'm now going to describe one such generalization, which is called some M-array PSK modulation. It's basically a generalization of QPSK with 4 constellation points. So here I have 8 array PSK. There are 8 constellation points. And I'm at a time selecting one of them. And because there are 8 points, I need 3 bits to select one of them. So maybe those 3 bits are just like what we did for QPSK. I can say that maybe if I get 3 bits as 0, 0, 0, I will send this particular constellation. If I get 0, 0, 1, I will send this point. Maybe if I get 0, 1, 0, I'll send this point, and so on. Why is this called phase shift keying? Well, because if I think of these constellation points as complex numbers, then you will see that when I change the symbol, I'm not changing the amplitude. The magnitude of all of these complex numbers are identical. They are all on the same circle of the same radius. But what I am changing indeed is the phase of the complex number, phase angle. So I am shifting the phase, and that's what it's called phase shift keying. That is all there is to it. This may seem like a very advanced modulation scheme, but this is all there is to it. Again, remember, this SI will be G1 of T. This SQ will be G2 of T. And I can either make G1 and G2 to be cosine and sine of the same frequency, that is one way to transmit M-array PSK. Or I can make G1 of T as cosine of 2 pi F1T, G2 of T as cosine of 2 pi F2T. That would be like BFSK. It doesn't matter. It doesn't matter what actual G1t and G2t waveforms are. What matters is that those two requirements have to be met. I should be able to write G1 of t as an electromagnetic waveform whose energy, if I measure over one symbol duration, it becomes 1. And G2 of t, again, its energy I measure over one symbol duration, it should be 1. So the exact waveform, whether it is cosine, whether it is sine, whether it is F1, whether it is F2, all of that doesn't matter. You have choice of what you want to keep as G1 of t and G2 of t. But what matters is that your choice has to satisfy those two requirements. That individual G1 and G2 should have unit energy over one symbol duration, and over the one symbol duration, their vector dot product should be 0. Okay? So that kind of allows us to use a wide variety of G1 and G2. Maybe, okay, here I'll tell you one more thing. So G1 and G2 don't have to be this cosine and sine, in fact. A valid choice, yet another valid choice, although it's not a very popular choice, but a completely valid choice for G1 and G2 is as follows. So this will hopefully convey to you that the exact shape of the waveform is immaterial. Those two requirements have to be met. And so I will draw as a function of time, I will draw this time axis. This is the time axis, and this is the voltage axis. So this is where I'm plotting G1 of t. And this is 0. I'll make this t sim divided by 2, and this will be t sim. So G1 of t is nothing but a rectangular pulse which starts from 0. So it is like this. Here I will use a different color. So G1 of t is like this. Starts from 0, and then it's just a rectangular pulse which ends at 0. Now, and over the length of this pulse, which is t sim, its level is constant. Now, for this one, I think you should be able to figure out very quickly, without doing any trigonometry, what should be the amplitude so that that first requirement is met. Who can tell me that?
1. 1.
No, if I do 1, if I integrate this rectangle over 0 to t sim, basically
So
the
1 by T sim.
1 by T sim.
yeah, but I'm squaring it, remember.
Okay, 1 by root 2 sim.
1 by root T sim.
Root T
Correct.
sim.
So it should be 1 over t sim square root of it. So the height is given by this expression. And so this G1 of t is a perfectly valid choice as one of the axes. You can make it x or y axis, it doesn't matter. But now the other function that we will have to use, which is again as a function of time. Sorry, I need to make this black. As a function of time, the other function g2 of t, I will make it like this. So it will start with some constant amplitude. It will go up to t sim by 2. And then at that point, I will make it exactly negative of what it was. And then at t sim, I will end it. So this again, I need to draw the right color so that you get the idea. So this is how this G2 of t will look like. This is a perfectly valid choice of G1 and G2, by the way. And again, by doing the same math in your head, if you integrate the area of this function after you square it, the only way you can make that area to be equal to 1 is if you make this level as square root of t sim, and then this also as negative 1 over t sim. So this individual G1 and G2, once I have this proper amplitudes, they are indeed satisfying the first requirement that they are unit energy signal, or if I interpret them as vectors, they are unit length vectors. Now, what about the second requirement? Do you think the second requirement is going to be met with G1 and G2?
Yes, sir.
It will be met. Why? Because once I multiply G1 and G2, I'm actually going to get a shape which will look like this G2. Because G1 is just a constant all throughout. So once I multiply it with G2, this shape of G2 doesn't change. So the product signal G1 and G2, it is going to look like this G2, except its magnitude will not be square root of 1 over T sim. It will actually be 1 over T sim because the other square root of 1 over T sim comes from G1. So the product G1 and G2 will look like this function. Now, if you integrate the area of this is positive area, this is negative area, they both are equal, so they will cancel out, you will get 0. So coming back to this Emery PSK, you can have G1 and G2 like what we just now looked at. Now I have two questions for you before we conclude. One question is, fine, so you did this transmitter, which is, we can call it 8 array PSK. There are 8 symbols here. And you came up with this particular constellation diagram. What will be your decision rule at the receiver? That is my first question. And my second question is, what is the probability that if I transmit this symbol, let's say symbol 2, at the receiver, it will get confused as symbol 1, which is this. Okay, so these are my two questions to you. I'm going to take a very short break, maybe for a few minutes. And then okay, so does anybody have answer to any one of the two questions?
The error probability will be u of a sine 22.5 degree upon and not by 2 root.
Good, good, good. Remember, the error probability depends only on the distance between the 2 points. So that distance is what you would need to calculate. If you connect this two points, what is the length of this line? That is what you have to determine. Now remember, we have said that the distance from the origin is square root of ES. So if you look at this triangle, the length of these two sides you know. And this angle also you know. It is going to be 45 degrees. Now, one very simple way, and a very accurate way is to actually calculate the length of this side of the triangle when these two sides have length of square root of ES and this is 45 degrees. A very approximate way which will kind of give a very similar answer is that you approximate this line, this straight line, by this arc. Now we know that the length of the arc is nothing but the radius times the angle. So you can even actually make it square root of ES times pi over 8. That will give you an approximate answer. The actual answer is what was just now mentioned. It is going to be square root of ES. The distance squared is going to be ES times sine of 45 degrees. So that in that formula, Q of square root of D square divided by 2 and naught, I will say that where D square is going to be ES times sine of 45 degrees. So that will give me the probability that when I transmit this symbol, it gets confused as this symbol. Or it gets confused as this symbol. Both are going to be equal probabilities. Okay, so that is the answer. What about the decision regions? How should I draw the decision regions?
That are angle bisectors of that vectors.
Right, so there will be perpendicular bisectors of all such lines that I would draw connecting two consecutive symbols. And if I draw perpendicular bisectors, all of them will have to pass through the origin. And so they will look like the slices of a pizza. And if I'm transmitting a particular symbol, let's say symbol 2, then this shaded region is the decision region for symbol 2. All the points that I get at the receiver, which fall in this blue shaded region, I will demodulate them as symbol 2. Because all of these blue points are closer to symbol 2 than they are to any other symbols. Right? So at the receiver, I might, because of the noise, I might get any two-dimensional vector. If I get a particular two-dimensional vector, and let's say it happens to be a vector somewhere over here, let's say. Then I will say symbol 2 is the most likely to have been transmitted. If it ends up being a vector somewhere over here, then also I will say it is symbol 2 which is most likely to have been transmitted. So now, let us wrap up this particular topic by drawing a diagram. It's actually a block diagram where we will summarize what we have learned so far. So at the modulator, we take an incoming sequence of bits, and we take k bits at a time, small k. So for BPSK, k is equal to 1. For QPSK, k is equal to 2. For that 8 array PSK we just now saw, k is equal to 3. And the way to show that is our incoming bit stream, we are kind of doing serial to parallel conversion, meaning we take a block of k bits at a time, and those k bits become the input to our bit to symbol mapper. We have seen what the bit to symbol mapper looks like for BPSK. It is nothing but 1 getting mapped to plus a, 0 getting mapped to minus a. We have also seen what this particular block, bit to symbol mapper, how it looks like for QPSK. From the constellation diagram of 8 array PSK, we can also define what it will look like for 8 PSK. Basically, there will be 3 arrows here, 3 bits. And at the output, we will generate in phase and quadrature coefficients or the coordinates. So this is the generalized diagram of a digital communication scheme. And I'm going to simply draw now a wide variety of modulation schemes. This is QPSK, which we have already seen. This is 8 array PSK. K is equal to 3 bits, and so there are total of 2 raised to 3, 8 symbols. So M is 8, K is 3. This is 16 array amplitude phase shift key. Here I'm shifting both amplitude as well as phase because I have 3 different circles. So I'm changing amplitude, and within one circle I am also changing phase. And I have kept 16 points, so M is 16, and therefore I take 4 bits at a time, as you can see here. 0011 gets transmitted as this constellation, and so on. Now 16 array APSK is also quite similar to what is known as 16 array quadrature amplitude modulation. So I will write this. This is called 16 amplitude phase shift gain. That is the short form. The short form of this is APSK. Amplitude phase shift key. This is 16 array quadrature amplitude modulation. So that is the full form of QAM. So again, I have 16 symbols. M is 16. K is 4. I take 4 bits at a time. If the 4 bits turn out to be 1000, then I transmit this symbol. If they turn out to be 4 zeros, then I transmit this symbol. So this is my bit block to symbol mapper. And then I can have 64 array QAM where each symbol now carries up 6 bits. It's like a big truck. Every symbol has 6 bits worth of information. And the diagram will look like this. And I can just keep on generalizing. I can have 256 array QAM. I can have 1024 array QAM. What will be the number of bits getting transmitted in 1024 QAM?
And
Yeah, it will transmit as many as 10 bits at a time. And this constellation diagram look very busy. It will have 1024 points. And there is no reason why I have to make it a complete square. I can put those 1024 in any manner I like in this IQ plane. I can make it a rectangle instead of a square. I can even make it a complete circle. I can put 1024 points along a circle. Then it will become 1024 array PSK. Or I can have multiple circles. Maybe I put those 1024 points carefully along 4 circles. Then it will become 1024 array amplitude phase shift. Or I don't even have to be using circles and squares and rectangles. I may want to use ovals, for example, if that is helpful. Typically, it's either PSK, APSK, or QAM. Okay. Typically, people don't use strange geometry like ovals or I don't know, pentagons or hexagons or things like that. Typically, it is circles. It is either just one circle, which is PSK, maybe a combination of circle, then it becomes APSK, or it's just rectangular type of arrangement when it becomes QAM. The nice thing is that now you have understood, hopefully you have understood the whole of digital modulation schemes, the whole gambit, the whole plethora, the wide variety of the ways in which your digital modem might be designed. So you have understood that. So that is one thing you have understood. The second thing that you have understood is, given a particular modulation scheme, what receiver design should look like. The minimum distance demodulator you have understood. If I ask you design minimum distance demodulator for 64 QAM, you should be able to tell me at least kind of a pictorial way of answering that question. So that is the second thing you understood. And the third thing you understood is how that modem is going to perform, at least in terms of getting confused as some nearby symbols. Okay, so all of that we have been able to do using this geometric. So I will end today's lecture here.